Welcome back, everyone. In the previous video, we discussed a little bit of an introduction on synchronization primitives, and then we looked into the advantages and the features that atomic variables provide and how they are implemented internally in the Linux kernel. Then we looked into semaphores, the how to use it, the initialization, the acquiring and relinquishing of semaphores, and how all of those are implemented internally in the Linux kernel. In this one, we're going to deep dive into the Mutex synchronization primitives and all of the similar things here. So let's get started. Right, so one of the things that we read theoretically about mutex is that it's similar to a semaphore which is initialized to count equal to 1, meaning that the resource that it's protecting is 1 in number. So you might have read many places that a binary semaphore, a mutex is basically a binary semaphore, and that is true to one degree, but there are some changes and differences even theoretically and especially in the Linux kernel's implementation of mutex as when they are compared to the implementation of semaphores that we discussed in the previous video. Right, so one thing which is different of how mutexes work is that it has a sense of ownership. Right, what that means that only the owner who has the mutex can unlock it. Right, one more thing that comes up with in terms of Linux implementation of the mutex is that it creates a possibility of avoiding context switch. What that means is, if you recall, and if the discussion on semaphores, then when a task was going to acquire a semaphore which was already acquired, which was not available, the first thing it did, the very thing immediately after checking whether the semaphore is available or not, what it did was it added itself to the wait list and went to sleep and scheduled itself out. Right, and this is one big difference between mutex and semaphores in the Linux kernel implementation, where in mutex there is an intermediate phase where if the mutex is not available and a task is trying to acquire it, it basically tries for a little while and waits for the mutex to be available before scheduling itself out. And this phase is basically called optimistic spinning. We will look into the details when in some time, but what it basically gives is a chance for the task trying to acquire the mutex to avoid this very expensive context switch and preempting out and in later back in. Right, this is one big difference. There are few more advantages of how the mutex is implemented in the Linux kernel. It things like it basically has a number of check where the memory where the mutex is residing, if it's freed, then you get some kind of a debug log where you can basically easier to understand that something is going wrong. There are various other reasons, and if you go through some of the blogs and writings, you would see that for a large number of cases it is usually recommended to use mutexes as compared to other synchronization primitives. Obviously this applies only to the category of the use case. If you actually want a lock which for a very small period of time, then the category changes and the recommendation goes to spin lock. Or if you have like a reader heavy and a writer low writing lock kind of needed, then you maybe go to a reader writer lock or an RCU. So, but not in the same category. But if you are in this category of a long held lock that you can hold for a long time and you're trying to basically protect a critical section, then mutex is one of the popular choices that is recommended. Let's look into the mutex structure that the Linux kernel provides. I have removed a lot of code from here because they were some of them is relevant to debug logs. Some of them is like a log dependency map for debugging when but and that which is not relevant to the session. So and they would just add clutter. So the important members to see right here is the owner is basically the member which decides whether the lock is available or not. So how does it do that? If it is set to 0, that means that the lock is available, and if the lock is not available for an acquired lock, it is set to the pointer to the task struct of the thread holding the lock. And this actually creates a sense of ownership where a mutex you can understand, you can find out who's holding the mutex by using this owner variable parameter member of the structure. Besides this pointer to task structure of the owner, this owner member of the mutex structure also holds some important bits. So basically the pointer to task structure only uses a certain length of the bits that are there in this atomic long, and there are free bits that can be used, and the mutex implementation takes this advantage and uses I think 3 or 4 bits to implement some functionality. And we will see these bits, we will discuss them, see these bits and how they are used internally. But just to keep in mind that the owner member in this structure not only holds the pointer to the process holding the mutex, but also holds some important bits, and these bits actually provides a sort of communication in between tasks which are waiting for the mutex to become available and tasks which are which has acquired the mutex and is going to be releasing it. So we will see all of this in detail in the later slides. Right, so the next member's wait lock is wait list, serves the same purpose as in the semaphore structure that we discussed in the previous video, where the tasks which are waiting for the mutex gets added to this wait underscore list, and the once this list manipulation happens while this wait lock is held, just to make sure that the manipulation, the concurrent access to this list is safe. Let's move on to mutex initialization, and to initialize the mutex init macro can be used, and this macro ends up calling the underscore underscore mutex underscore init function, and this is how this function looks. So the first thing it does is it sets the owner to 0, which basically sets the mutex to be free. Then it initializes the spin lock and the wait list. So one thing which I missed in the previous slide is this OSQ lock, which is basically an MCS type of lock, a little bit of variation of a spin lock. This is used for that special step that I discussed in the beginning of the video about mutexes, where it doesn't go to sleep right after checking. We are not going to delve into the details of this particular lock. Maybe in a future session we will, but we just have to understand is this lock is used to manage this waiting of the task which is trying to acquire a locked mutex. Right, moving on to acquiring a mutex. Now acquiring a mutex is sort of done by a mutex lock, and this is how the function looks. It's pretty simple. It first tries a first try lock, and it's a simple one which uses atomic compare and exchange to set owner to the calling struct, right? And if that fails, then it tries the slow path through this function called underscore underscore mutex lock slow path, right? So one thing to understand here is acquiring a mutex through a slow path is a complex affair. Uh, this there's a large number, so the main function that we just discussed in the slow path is pretty big, and it has a lot of uh, uh, mini functions that it calls. And as so what I decided to do is, first I will be going through these concepts that happens and the steps that the slow path takes in theory, just to give an idea of an overview of what happens. And when I start discussing it in detail in code after this, it will be easier to understand and map which part is doing what and how they are related. I am I'll be going to try my best to make this easy and simple for everyone to understand. If there is still any confusion, please comment below or write me an email or a message, and I will be happy to explain it further. So, one thing to point out here is the common mutex here does not employ what is called the wound and wait technique, right? So there are special there's a special technique called wound and wait, and you can see it in the slow path code. Some variables and functions prefixed with ww, and they are basically for a very for the common mutex that we are discussing here. These are emitted out and set to false. So while you're going through your slow path function yourself, you might come across this, and but we are skipping all those portions in this current session. Right, so coming back to the matter at hand. So the general sequence of the slow path for mutex lock is as follows. First, it's gonna try to acquire the mutex. As simple as that. It's gonna think that maybe we failed previously, but we're gonna try it again. And you would see this pattern again and again, that every now and then the code says, let's try again, let's try again. Even though we just tried to acquire the mutex in the slow path, in the fast path, we're gonna try to acquire the mutex again. Right, and if that fails, then this is the important step which differentiates mutexes and semaphores, where it's going to try to spin and wait for the owner who holds the mutex to release it. Right, we're gonna look into this in detail a little bit later, but let's move on to the next step. And if that also fails, the second step fails, then it's gonna do what a semaphore does. It's gonna sleep. It puts itself to sleep, and when it wakes up, it's going to try to acquire the mutex again. If it fails again, it's going to loop this last step again and again. Right, so during the last step, the thread executes basically a similar lock handoff like semaphore. Right, I know I'm referencing semaphore a lot, but maybe you can go to our channel or the video list and playlist and watch semaphore again before coming here. It would be a nice thing here, but I'm gonna explain it independently. What this means is, the task which is waiting to acquire the mutex is gonna get it by the task which holds it, which is already holding the mutex. While it is releasing it, it's gonna get moved to this previous task by a sort of communication in between, and that happens through these special bits that we discussed in the beginning. We will see all of this in action in a while. Right, so let's move on to the 3 steps that we discussed. We're gonna do this one by one. We're going to look into the functions and try to make sense as best as we can. Right, so the first step, the function used in that step is this underscore underscore mutex try lock common. Right, one thing special to keep in mind about this function is that it returns null on success, which is uncommon in the way functions are return valued are standardized. Right, one more thing to notice in this function, maybe when you go to the next kernel code yourself, is there is a param called handoff, and for this first step the param handoff is set to false. We will see when this is set to true and what that significantly means. But to keep in one thing to keep in mind right now, for the first step it's set to false, and that means the mutex trial or common function becomes very simple. And this is what is relevant to us right now. For the first step, the things before else is relevant when handoff is set to true, and in another case which we'll see later. Right, looking into this code, if let's suppose we will look into two scenarios. If let's suppose the task, so not the task, if let's suppose the mutex is free, so this else that we are seeing here, this branch will get hit if the mutex doesn't have an owner. And the positive and the optimistic case here is that the mutex doesn't have an owner. Maybe it got released while in between the fast part and this slow path first step code. It doesn't have an owner. What it's going to do is it's going to set task equals to task equals to current, which is the current pointed to the current task structure, and then it's going to try this atomic compare. And if the task and the current is equal, you can see this line here, and the second if, then it returns null, meaning that the mutex was acquired. Right, so this is the positive path where you actually acquire the mutex, and but that is not interesting to us. Let's forget about that and let's think that it didn't acquire the mutex. Right, then as I mentioned, this is the first and the simple step. It tries to acquire the mutex and we failed. Now let's move on to the next step, which is the optimistic spin. And for the next step, the function used here is optimistic mutex underscore optimistic underscore spin. Right, and as I mentioned, the idea here is to spin and wait for the lock to become available, for the mutex lock to become available. But we cannot do that for a long time. We have to set a criteria, and this wait, spinning and waiting. So one of the things to notice is, why cannot we spin and wait? Because the longer the time that you're spinning and waiting for the mutex to become available, the CPU that you're spinning on basically is sitting idle while doing nothing. You just wasting CPU cycles, and you don't want to do that for a very long time. So you have to have a criteria where you move away from the second step and go to sleep, and let another process take over the CPU and do its work. Right, so this criteria for how long to spin is gonna happen. There are two things to check. If the current task who's trying to acquire the mutex has been signaled by the scheduler to schedule out, maybe its time slice has expired or something. If it has been signaled to schedule out through this like reschedule function, then it's gonna stop this optimistic spin and move to the third step. And the another criteria here is, if the task which is holding the mutex, for which we are waiting for, if that task is preempted out. Right, now what is the rationale behind this? Is the rationale is that if the lock owner is running, then it is likely to release the lock soon. Think about it yourself. If the task is running with a mutex held, the probability of that running task executing lines of code is that it's going to come out of its critical section and release the mutex, and then you would be able to acquire it. Hence you would wait till that point. And when you look at this optimistic spin function, this is the most relevant part of the code, where it checks these two things. It checks whether the current task needs rescheduling, then it returns, and then it gets the owner, and it checks whether the owner is on a CPU or not, which means whether it's running or not. If that fails, then also it comes out of the second step, which is this optimistic spinning. So let's suppose we failed here also. Right, let's suppose the task trying to acquire the mutex failed here because maybe it was scheduled out by the scheduler. Right, so now what's going to happen is it's going to move to the third stage, and that stage happens in the same mutex lock common function that we have discussed earlier. Oops, I don't know what happened. Okay, coming back. So in the third stage, just like in semaphore, the wait lock is acquired, and to protect the wait list, and then the task is added to the wait list, and the state is also set to task uninterruptible, and once those things are done, then the task is scheduled out, right? Remember, this is the third stage where you try to schedule the tasks, try to schedule itself out, and then when it's woken up again, tries to get the mutex again. Right, so now the fun part starts, where what happens when it wakes up again on the third step, right? So this is a small piece of code on what it does when it wakes up. Is first it checks that whether itself is a waiter, is the first waiter or not, right? If it is a first waiter, then what it's gonna do is, so what it's gonna do is, whether it's a first waiter or not, whether it's the first variable here is true or not, it's a bool that is sent to this function called mutex try lock or handoff, right? And if it is the first task in the wait list, meaning this first param that we see in this code is equals to true, then the function, this mutex try lock or handoff function, is gonna mark the mutex for handoff. And this is basically a bit, one of the bits that we discussed right in the beginning of this session. And this handoff bit is basically used when the mutex is unlocked. And what we're gonna do here is, we're gonna see a little bit more about this handoff, and then we're gonna jump into mutex unlock path. And as we discuss this, we're gonna see how this handoff bit is used by the task which is releasing the mutex to signal the tasks which are waiting for the mutex, and for them to pick up when the mutex gets released by the other task, right? Right, so we're gonna come back to this once we are discussing the mutex unlock slow path. Just one thing to notice here is this is the code excerpt from the mutex try lock or handoff part, and let's suppose the caller task was the first in the waiting list. That first boolean is gonna get translated to this handoff in the else if conditional check, and what that's gonna mean is it's gonna set this mutex underscore flag underscore handoff flag, and this is what it's going to pick up later on the mutex unlock side. This piece of code actually has a few more flag checks and everything, but what I'm trying to do is I'm not trying to show everything in one go to overwhelm the viewers. What I'm trying to do is I'm showing just the part that is relevant to this particular call, and we're going to come back to this later, when after the mutex unlock slow path, when we have more context about that particular piece of code. Alright, so moving on to the releasing the mutex section. And releasing a mutex can be done by calling the mutex underscore unlock function. And just like the mutex lock function, it has a fast path which calls the function underscore mutex unlock fast. And this is how it looks, which tries to do an atomic long try compare exchange release. And the thing to note here is that this is gonna fail. So if you remember that the owner member of the lock here is set to the pointer to the task which is holding the mutex, that means that this is always gonna succeed because it compares with current, but that is not true. What's gonna happen is, if you remember the tasks that are waiting, they basically, what they do is they are changing or setting bits depending on whether there's a waiter or not, and whether there is a handoff that is needed or not, just like we discussed. And what's that gonna do is this lock owner pointer is gonna get changed a bit because some of the bits got changed, and this atomic long try exchange is gonna fail. So here the thing to realize is that this would pass only if there is no waiter who has set any of the bits in this lock owner member, right? And it's gonna fail if something has set, and if that fails, it's gonna go to the mutex unlock slow path. So the slow path calls the function underscore underscore mutex unlock slow path. So it does a number of steps, and I'm gonna try to name them all one by one. First, what it does, it tries to release the lock, right? And this, it not just tries, it releases the lock, and this releasing of lock happens only if there is no handoff bit. Why this is relevant here is if there is a handoff bit, that means this slow path can successfully hand off the mutex to a task which is waiting for the mutex, right? Because that task is probably the one which set this handoff bit. Hence, there is no need for the mutex to get unlocked, and it's gonna skip that. If let's suppose there is not a handoff bit set, then the mutex gets unlocked through this unlocked or released through this compare exchange. So once that is done, the second part of this function is executed when there are waiters and or handoff bit also, right? So one thing to note here is that a handoff bit can only be set when there are waiters, but the vice versa is not true. What it means is that if you remember our third step in the mutex lock slow path, the task first adds itself to the wait list, and then it sets the handoff bit. That means there is a time window in between where there can be a task in the wait list, but the handoff bit is not set. What that means is that there could be waiters in the waiting list, but the handoff bit is not set. This is the reason why if there is a handoff bit set, there is for sure waiters, and hence in the second point in the slide we see that in case of a handoff bit is set, the function tries to hand off the mutex directly to the waiter and not try to release it through a compare exchange. Right, so discussing the second step, as I mentioned, the function mutex unlock slow path, it picks the first waiter from the wait list, and if you see, it does a list first entry which basically picks up the first waiter, and it adds it to a wake up queue. It also wakes it up later in the end of the function, but before that it checks this mutex flag handoff, and if that is set, it calls the underscore underscore mutex handoff function. And that is the last part where this handoff that we discussed from the task who had the mutex and is trying to release it happens to the task who's waiting and had set the handoff bit, right? So the last part is this function called underscore underscore mutex underscore handoff, and this is only called, as I mentioned, if the handoff bit is set. And this is the most relevant part of the code here. If you see, what's happening is this function is basically creating a new long variable, and what it's doing is it's basically setting it to the task which was dequeued from the wait list. If we move back a bit and see that mutex handoff was called by the second variable, which is next, which was dequeued from the wait list, and that wait list next is basically pointer to the task struct of the process waiting, and this function basically is creating the new variable with that pointer. And if there is a task, then it's gonna basically sets a new bit here, which is a pickup bit, and this bit is the something which is gonna signal the task waiting that a mutex has been handed over to it. We'll see how in the next slide, but next we see in the compare exchange that the owner is overwritten by new, which is basically the pointer to the task struct of the task waiting in the waiting and was dequeued from the wait list in the previous function. Right, as I said, it also sets the pickup flag. Now we'll just move back a little bit to try to revisit the mutex log slow path to understand what happened here, what how relevant, like now we know a bit of the code from the unlock slow path, so it would make more sense now to us, so hence we're revisiting here. So just to recall, when the task was trying to acquire the mutex in the wait list, it calls mutex try log common with the handoff param set to true. Right, we've discussed this. I'm just trying to reiterate here so it comes to everyone's mind. And this is the bit of code that I held off previously, and now we can look into this and make sense, right? So we've seen the handoff bit part, where if the function is called with handoff equals to true, it sets off the handoff. But previous to that, what it does is, when it's trying to acquire the log through this try log common, it checks whether the flag has a pickup bit set or not. Just like we saw previously, the pickup bit is set when the task holding the mutex has unlocked it and passed it to one of the tasks from the waiting list, basically the first task from the waiting list. Now the task running this piece of code knows that the mutex has been unlocked and is handed over to one of the tasks, but it does not know whether it is that itself or some other waiter which was ahead of it in the queue. And that test is this task, which is the second if nested if task not equal to current. If it is not equal to current, basically means that the task to which the mutex was handed over is not itself, but it is someone else, hence it breaks. If it is equal to current, that means the mutex has been handed over to the running task and it clears the bit, and later in the function you see that it returns null. And if you recall, this function returning null that means it's success, and that's how the mutex handover successfully happens from the task which set the pickup bit to the task which had set the handoff bit. Right, so not relevant slide here, but you can send your questions, email us or write a message to us in LinkedIn, or just comment your questions and thoughts below. And if you have anything that could be improved from my side. So this is a little bit about us. Email us if you have any questions. Follow our page in LinkedIn for news about upcoming sessions, and we also have a mentee program in planning. So if you are interested in that, please reach out to us. Follow our YouTube channel, and we do plan to have a blog or a website soon. We are a bit thin on resources, but we will have it soon. Thank you for watching. And as I said, we will have some more sessions on other synchronization primitives soon, and will be added to this channel.